So today's going to be our last official lecture and any topic that we're going to be getting into. And next week I'll be just doing review for our test. It'll be that following Thursday. So we're going to do a lab this week. It's kind of just a demo lab. We're going to be going out and talking about data collectors today a little bit. Pretty easy topic. So that may not take too long, but I also want to just go over some other things that you may have questions about. So I do have under that week 14, that should be available. So we're going to look at electronic data collectors and data types transferring, but I have a lot of good information out here. There's some things about like bearing distance. I'll talk about that, but we're not going to be necessarily going over any of this stuff too much. In other words, you're not going to be responsible for it. But we will talk about converting raw coordinate data into spherical coordinate data. That's one of the things that your data collector will do for you. Actually, your total station does too. And I also want to finish up some things from other labs. So there won't be any kind of write-up or anything. It's just a participation lab this week. I am going to have you guys come in at the normal time, and then George Armstrong's going to come in. We're going to do a little bit of GPS, show you the data collectors and those kind of things. I'm going to do, for the morning class, I'm going to do a little bit of going over stuff with you guys. In the morning section, George will be coming in at 11. We'll be doing the lab from 11 to 12. So it's just basically showing up and you're getting credit for it kind of thing. There's no write-up. The afternoon, then they're going to go from 12 to 1 with the demo, and then we'll follow that up with doing some other issues, talking about some of the stuff that we need to. In other words, kind of trying to get you guys prepped for the upcoming test. Okay, does anybody have any questions on that? We'll meet at normal time, and then we'll basically just be outside for an hour each group, and then we're going to be inside for the rest of the time. So do make sure that you bring questions, books, calculators, so that we can go over stuff. Okay, any questions?
I'm good for now.
All right, so first thing I want to do is go over that quiz, just go through the exam or the problem with you. There were quite a few that you didn't even do the quiz, so I'm not sure what's up with that, but you're going to have another quiz this weekend too. So, those are things that are going to help you deal with the stuff you're dealing with in your write-ups, whatever, and then also you'll probably see some of this on the test again. So let me switch over here, and I will say this: the people that did this did better on this than we did on the last one. So this was dealing with a vertical curve. Let me just draw it out, and we'll go through it. If you have any questions, certainly don't hesitate to ask. Okay. So we had a quiz that was given. It told you had a grade, a 2.5% grade coming down, and a 1.75% grade going out. So it met at a PVI location, and you knew that your curve was 500 feet long. So what we have is, if we look at this in the profile, what we're seeing is something like this. So if we labeled everything, you were given a PVI, point of vertical intersection, it gave you a station of 27 plus 50, I'm sorry, 2725. And the elevation of that PVI was 546.96. So what we had to do was solve the location and the elevation of the low point. So what we also know is that this guy is 500 feet. Okay, so 500 feet, 250 feet left and right of that. So this would be called my BVC, and this is my EVC. Okay, so we have a negative grade coming in, and we have a positive grade going out. So we wanted to know low point, station, and elevation. Okay. So in any problem like this, which is very typical with those givens, the first thing you need to solve is your BVC. Now you don't necessarily need the EVC unless you want to check it. Some people did solve that, and but if you did need that, you could solve it. But we really, for this problem, only need the BVC. So we need two things: the BVC station and the BVC elevation. So the station is going to be equal to that PVI station minus half of the distance L, because we're dealing with what's called an equal tangent curve. So it's 250 feet this way and 200 that way. So what that'll do is that'll give you the BVC station of 24 plus 75. The elevation is just simply taking the elevation of the starting point, which is this guy here, and we're going to go up this slope, so you're going backwards on that, so you're subtracting a negative. So what that's doing is actually making that a positive. In other words, you're rising. And the distance we're traveling there is 250 feet, but what I'm going to do is I'm going to put this percent times stations, and that'll give me feet. So by doing that, that gets me an elevation of 553.21. Now notice this elevation has to be higher than this. Okay, so if it doesn't, your picture's wrong, or you're thinking about it wrong. Does anybody have questions about that? Because that's pretty important. Okay, so this is, if no questions, then this is the starting point. Okay, so we've got that. So now we need to write the equation of this parabola. Okay, so you got a parabola coming in here. It's got a low point somewhere. This, by the way, is not the low point. Does anybody know why this is not the low point?
That's just the intersection point of the two tangents.
Right. So one answer is that it's not on the curve, right? The curve is actually above it, correct?
Yes.
Okay. The other answer is that you could have this at that station, but it wouldn't be at that elevation. But how could it be at that station? Anybody know how the low point could be at the PVI station?
Would that be if the slopes are equal?
Exactly. Oh, they'd have to be opposite sign, right? So you'd have to
Yeah.
have a -2.5 and a +2.5. That's true. But because this is different, it's going to skew it to one side or the other. Okay. So you can recognize that. Okay. So that was good. So the next thing I need to do is write the equation of parabola. So the equation of parabola, I've got two things I need. I need R and I need the BVC, which I already have. So R is grade 2 minus grade 1 divided by L, where the grades are expressed in percents. So grade 2 is 1.75 minus a -2.5, which really is going to make that a plus. And the L is expressed in stations. So instead of 500 feet, I'm using 5 stations. And that gives me a positive 0.85 value. So what that's telling me is that this is a sag curve because this thing eventually is going to go up. That's what the plus indicates, okay? What we call an increasing function as we look at this. Everybody okay with that? Many of you guys that didn't get the whole problem right did at least get this right, so this is critical. And so a lot of you guys did that well. So the next thing is to write the equation of parabola, and that's basically y is equal to r over 2 times x squared plus g1x. G1 is a -2.5, so you just plug that in for g1x, and then you add to that the BVC, okay? So you can notice if you blow any aspect of that, your whole curve is wrong. But this would be the parabola, or the equation of the parabola that is occurring from the BVC to the EVC. So if you're looking at where this is valid, anybody tell me what stations that would be valid from to? In other words, you could use x from 0 up to, what would be your maximum value of x? It couldn't be any higher than 5. Okay, so it has to be from this 0 up to that, which would be 5. Does everybody see what I'm getting at?
Yeah.
So what we need to now do is solve the value for x. We don't know what that is, okay? So there's an equation that we talked about last week and in your book that says that your x value is going to be equal to G1L divided by G1 minus G2. That can also be written as minus G1 divided by R. They'll give you the same answer, okay? So either way, I'm going to back it up because I think most people on the test did this. So G1, we just plug that in. That's a negative 2.5 times L in stations, which is 5. And then we have a negative 2.5 minus a 1.75. So this value can't be greater than 5 and it can't be less than 0. So if you come up with a negative answer or you come up with something greater than 5, that doesn't work. So when you do the math, notice you got a minus divided by a minus. That's going to give you a positive number. So at least that comes out to be right. You should get in the order of this. And this is in terms of stations. Okay? So you just plug that in right here and run that through the equation. And what you'll get is the low point. So when you do that, the math through that, plugging that in, squaring it, multiplying it, taking that times that, and then adding those all together, you should come up with a number. And this is the number you should have been getting. And notice this has to be higher than this. Okay, it can't be any lower than the PVI, but it does make sense. This is lower than this, and it's going to be lower than this as well. Okay, so this would be the one answer that we were looking for. And then the other answer is the location. And some of you got the location just fine. So a lot of you guys did this and just didn't do this. That was pretty common, actually. So the station is equal to the BVC station plus X. Okay, so the BVC station is 2475, and we're going to add X, but we have to use that in feet. So we're going to convert that to feet. That would be 294.12 feet. So all you're doing is just moving your decimal place over, okay? So when I add that 294.12, what I get is 27 plus 69.12. So if this was a case where you were looking to place catch basins, this is the station you would place them at, and this is the elevation they'd be at. So if the station here is the PVI is 2725, the low point is someplace over here. Okay, so that was that problem. So that was a good problem. Like I said, a lot of you guys have really tackled it well. Okay, some people just didn't do this piece of it at all. A lot of people got the station. That was really good. Although some people that did get the station calculated this correctly, but got to recognize that this is in station, so you have to convert it to feet to do this. Okay, so that was also a common mistake. But I had people that drew that parabola. Here's what I had a couple people do. Drew this grade like this and that grade like that. How are you going to get a high? How are you going to get a low point out of this? Right? I mean, if you look at your parabola, it's going to be up here. That would be a high point location. So in other words, people mirror imaged it. All right. Any questions on anything? This was much better than last week. All right. No questions before we move on?
I got a 9.5 out of 10.
Yeah.
But I don't remember what I got wrong.
Well, I'll bring your stuff Thursday. Is that Jake?
Yes.
Let me check yours real quick because I have yours real quick. I can. When you plugged this number in for your equation, you plugged in 5 for this one for some reason.
Oh.
So you plugged this in correctly and you plugged this wrong, so it blew that answer. So
okay.
I mean, you had everything else essentially right. Had you used the 2.9412, you would have had 100%. So.
Yeah, I think I was running pretty tight on time, so I guess I just rested.
I mean, I get that, and I'll be honest with you guys. If you guys just give me the worksheets, I don't even necessarily look at what's on Blackboard, but I do have to have some kind of, I have to have some kind of accountability. So that gives me that, that accountability. I certainly don't like doing stuff online. I'd rather do stuff in person. That's why our final test is going to be in person instead of this one. But we are going to have one more quiz on Blackboard this weekend. Okay. And so those of you guys that didn't do that quiz, make sure you're doing it. At least try it because you're going to get something. Okay. If you try it, you're going to get something. All right. Anybody else questions? Okay. Well, we'll move on then. So does anybody have any questions from last week's lab or material over that? So we can wrap some stuff up. Now I'll be able to answer some questions on Thursday as well. So let me go back here real quick. Let me open up, before we go, let me open that up and see if there's anything out of the profile section. So we went through, we've done the lab. I hope you guys got to see everything that was going on out there. We did a pretty neat project. Oh, I'm sorry, this isn't the one we did last week. But is there any questions on this one before we move on? Got your profile? Anything else? There were a few questions to answer in this. Okay. Well, how about last week's lab? That was a good one too. That was a nice intersection routine. Let me open up that handout. Okay, any question anybody has here? There were two different groups. One group, by the way, that the morning group laid out this intersection, the afternoon group laid out this intersection. Okay, so make sure that when you're following the information, you got to use the grades for the one intersection here and one here. Okay. So basically this diagram, let's see. This is giving you your profile information. That's your profile information for your intersections. And then there's another one that looks like that for the other intersection, but make sure that you're getting the right one, okay? No questions on any of this, anybody? Okay, how about these typical sections? Does anybody have any questions on this? Because I should probably go over some of this. I'll probably follow up with some of that actually on Thursday. Anybody questions over anything on this typical section?
I'm good for now.
Okay, anybody else?
I had a question on 5 and 6, not on this
Okay,
lab.
we can scoot back. Let me go back to that, okay?
Okay.
Is that Carson?
Yeah.
Okay, hold on a sec. It was 5 and 6?
Yeah. It was the it was for to get the curb elevation.
Okay.
So on that sheet, I'm taking all my stake elevation from our level notes.
Yes.
And then I'm putting that in stake, and then I get the center line elevation, and then I either have to add 0.19, correct, to get the curb elevation.
Well, let's look at it real quick. Yeah, you're on the right track. Okay, so which typical section are you using here? Do you know?
The one to the far left.
This one here?
Yeah.
Okay, so notice what it says, that your top of curb is 2 3/4 inches below the center line.
Yeah.
So that means at the center line at this point, right? You are 2 3/4 inches below both left and right of that center line. Okay.
Yeah. Yep.
All right. So let me grab a piece of paper here and we'll kind of work this out so you can see a problem. And again, these are some questions that I will answer Thursday too, okay? Because reading these typical sections, it gets a little involved. So I understand that. So
Okay.
we have to first take 2 3/4 and do what with it?
Convert it to decimal.
All right. Well, convert it to, yeah, decimal's fine. 2 3/4 is 2.75. But what are you going to do with that number?
Divided by 12.
All right, that's what I wanted you to say. I need to get that in feet, right? So
Yeah.
we're going to divide that by 12, and that gives you
Oh, 0.02.
0.23. Did I do that right? Two
I
and a
think
quarter.
I messed up.
0.23 basically, right? So
Yeah.
that's basically 2 inches. Okay, little more. So
Okay.
so 0.23 feet, what you're doing is subtracting that number. You're subtracting that from the center line elevation is all you're doing.
Okay.
So if we go, let's go to the profile here. Okay, so let's look at the profile. All right, so for instance, if we look at the BVC, notice it gives me the BVC, can you see that, guys?
Yeah, I can see it fine.
Okay, so the BVC, notice what station we're at. It's at what?
0.0.
0.25, right?
Yep.
Okay. And you put a stake in at that point, right?
Yeah.
So you should have an elevation on those stakes left and right for 25. Now you have to make sure that you're following left and right, okay? Because that'll make
Yeah.
a difference. Okay, so what does it tell us that the center line elevation is at 0 plus 25?
I guess 592.98.
All right, so 592.98 is the center line elevation. And what are you going to do with that to get the curb?
You would add, or you would subtract 0.23 from it, right?
Right. So that would give me that curb elevation at that point would be 592.75.
Okay.
That's what I'm coming up with, right?
Um,
Check it.
592.75. Yep.
Okay, so that's the curb elevation left and right of that station. So now you have a elevation of the stake left and an elevation of the stake right. The difference between the stake elevation and the 59275 is your cut or your fill. So just pay attention to whether that stake is above that
Okay.
point or
Okay.
below it, right?
Okay. Yeah.
In general, you'll probably find that all the stakes to the left are pretty much going to be cuts,
Okay.
and all the stakes to the right should pretty much be fills.
Okay.
Yeah,
Does
that was the same
make
for
sense?
me.
Yeah, is that true?
Yes.
And now, remember what we said about this, that in reality, that's not going to be as big a cut or fill. Why is that true? You guys are probably getting pretty big cuts and fills, right?
Because they would
Yeah.
do they would come in before, and then we would do construction layout, right? Or
Right. So you see this red line right here on this.
yeah.
What does that red line represent?
That's
That's
existing.
That's
yeah.
existing. Well, if you're really doing curve, that red line is gone. You're going to be closer to this blue line. Okay.
Okay.
Because what they're going to do is they're going to come in and grade it, and they're going to cut way out left and right and have all those fills in place. So in reality, you would probably have no more than if you even had a half a foot cut and fill, that's a lot. Okay.
Okay. Yeah.
I mean, and most of the time they're going to be pretty significantly small. Okay. Because they're going to get that pretty well graded out. Does that make sense now?
Yeah, that makes sense.
So you literally are just going to go in at every station that we need to put a cut on and just subtract that 0.23 off of it. You know, that's going to be across the board.
Okay. And then do we start from 0 plus 65 because that's where the curve is starting, or that's where we're starting?
Where did you start doing your stakes?
We started at 0,
Okay.
0, 0.
Right. And we had this.
Okay.
Do you see this blue line right here?
Yeah.
Okay, that's where the curve starts, or the curve starts.
Okay.
But we actually placed this tangent in. So you should have 0, 25, 50, and 60, right?
Yeah.
So you're gonna grade the tangent and the curve.
Okay. All
But
righty.
we're gonna end at the PT because we didn't stake this piece of the tangent out following
Yeah.
that. So, okay.
All righty. Yeah.
Okay. Does that make sense?
Yeah, it does. Thank you.
Yeah, sure. So this is, this stuff is good stuff, guys. I mean, now, let's see, did I give you one of these things? I gave you a sheet. Maybe I don't have it in here, but there's a sheet that shows you, it shows you your cuts and your fills and all that. But just make sure, let me see if I can find it, because I thought I had one like that for you. Let me look in my.
Yeah, it's the roadway cut fill sheet.
Oh, okay. Well, use that because that'll just make it real simple for you.
Yeah.
Was that
Yeah.
was that in last week's lab?
I don't know about last week's, but it is in 5.6.
Is it? Okay. Well, it's not in that one for some reason. But yeah, use that cut sheet because that sheet will really help you put everything together. I think it might be. Let me check this one real quick. Yeah, I don't have it in there for some reason. But yeah, there's a cut fill sheet, right? So that's the one that you want to use. Okay.
Alrighty.
Yeah, that's perfect. All right.
We
Yep,
were
thank you.
using the Type 2 flexible payment, and the elevation for the curb was supposed to be minus 1.99.
Well,
Um,
did I just do the wrong one? Let's check
Oh
that.
no, his was different than ours.
Why
we had a
was this
different one.
different? It should have been the same. You guys did the same project. Let me
I
check
just
that.
remember this is the one that you did in class for us.
Okay, well, let me just check this real quick.
All right.
All right, so what this says,
It says part 2 use the Type 2 flexible payment.
yeah, you're supposed to use type 2 flex.
Okay, I see
Yeah.
it.
So that was my bad. Essentially what we just said is correct. We just used the wrong typical. Does that make sense?
Yeah.
Okay, so instead of 2 3/4 below, we're going to be 2 3/8. All right.
And I just rounded that up to 0.2.
Yeah, what's that come out? Let me check that real quick.
It was like 1.997, something like that.
Absolutely. Yeah, you're going to call that 0.2. They're never going to build it that close. Okay.
Okay.
So Carson, everything we said was correct. We just used the wrong typical.
All right.
Okay. And so instead of 0.23, you're going to be 0.20. Okay.
Alrighty.
Yeah. All right. So that's how these guys, by the way, these are such important little documents because they relate all of that stuff that's going on left and right, on the center line. So that was, I mean, I can get into more of this if you guys have questions, particularly out of last week's lab. You guys want to look at anything out of that? Because there's these other typical sections. This one, for instance, what this allows me to do is determine any elevation along this thing if I've got the information on it. See, so this is a good example of a true typical section. Actually, this is right out. That's a Hamilton County standard, unless they've changed it. I mean, they use this for years and years. Okay. Any questions? We're all good?
Good for now.
Okay, cool. All right. So if there's no question, you guys, if you have any questions, just let me know Thursday, okay? Because like I said, we're going to spend some time going over some of this before we go out in the field or after we go out in the field, one of the two. And so I want to make sure everybody's clear on this. It's not hard, but it's confusing, and it's just a little bit trying to visualize it until you get really your feet on the ground with it. It's a little tough, okay? All right, so let's go in to this week 14. You have, I've got some good stuff out here for you. We're going to be looking at this lecture material stuff. So go ahead, if you don't have that open, you might want to open that up. I have a bunch of other diagrams in here. Like I said, there's some things, bearing intersections and stuff. I'm going to explain that today. I'm not going to probably go over that at all too much. So I don't want you to be too concerned with that. I got some other supplemental material here. I'll probably open that up after the lecture. Some stuff that you can, there's solutions to some of these problems, but I really don't want to burden you guys with that stuff too much because we're just not going to do it. So I may not put that out there, but just also keep in mind, we will have a quiz. So the quiz will be open. I'll probably open it on Friday, and it'll be open through the weekend. Okay, so please try to make sure you do them. Okay. So I'm going to go ahead and fire up this week. So we're going to talk about electronic data collection. And I'm going to go through this quick because there's not a whole lot to see about this, but want to also kind of explain a little bit. We're going to be doing some GPS layout, just more of a demo, but it kind of uses this concept. So let me start from the beginning here. And if you guys have any questions, don't hesitate to stop me or ask, or let's talk about it. So electronic data collection is primarily the way probably most surveyors would work nowadays, or most, I should say layout people, because it's not just surveyors anymore. But this stuff happens at a wide level. And these are basically handheld computer devices that interface with your instrument. And you don't write down stuff anymore, essentially, with a data collector. Everything just goes straight from the instrument into the data collector itself. And then that information can be dumped into a remote location like your office. And your office could be in Toledo, by the way, and you're working down here, and you can send that stuff over the internet so those guys can get all the information and be working. So it's not like it used to be at all. And not too many people are taking hand notes anymore, that's for sure. So we'll look at data collector use, some of the data types that are associated with it, and data transfer. Now I have some other things in here, like I said. We're going to kind of just talk about it briefly, just to give you a heads up on it. And I'm sure that when we get out there on Thursday, we'll show you some of this stuff so you can kind of see the power of this. So a data collector, it's just a very, very powerful little supplemental device that we use with instruments. Now it is a separate cost item. So it's like if you buy a total station, you don't get a data collector with it. There is basically an onboard data collector in the total station, but it's not very powerful. So if you want to use another type, you have to pay for that. And those things are pretty pricey. They were probably anywhere from about $2,000 or up to maybe $5,000, depending on the software that they have and what they do. But these are used with total stations and robotic total stations. In fact, a robotic total station, you really couldn't work without a data collector associated with it. Digital levels, so if you're doing not the conventional optical levels like we're using, you can use a digital level. That uses a data collector to record all of your HIs and your rod readings. And then GPS receivers. Again, that's another thing that's going to be pretty dependent on a data collector. Now, the downside to all of this is if your data collector dies, just like your total stations, sometimes you can't even run things. So if you were out there with a robotic, you would pretty much be done for the day if you lost your data collector power. So those are some issues associated with them. So they're going to have a lot of advantages when you use them. And one of the things is they're going to eliminate human error, because when you're out there shooting distances, angles, and all of that, you're not going to write it down wrong, or you're not going to forget to write it down. So it's real easy to forget to write a measurement down back in the old days when we were writing everything by hand. And transposition, you know, you're reading 212 and you're writing 121. That happens all the time. And of course, that can just kill you, especially if it's a small transposition. So those are issues. Those won't happen because all the information is coming directly from the instrument. And of course, in the field, these things save time and money, actually both in the office and in the field, because you don't have to write notes down. And in the office, that was where they would really save time, because back in the old days when you had all these field notes, if somebody was out there generating a surface, taking, you know, they might be out there taking 1,000 shots in terms of angles and distances all day long. And that stuff then would be given to somebody in the office, and they would have to key that in. So you've got two places where you could have had errors associated with those numbers. One where the person out in the field wrote it down wrong, and the second place would have been the person in the office transposed it. Plus, taking all those notes and plotting them in the office by hand, or even putting it into a computer, is going to take hours. So, you know, this stuff really does save time and money and mistakes.
Is that field to finish?
Well,
is that what
yeah,
you're mainly talking
basically,
about?
the only difference there, Casey, is when you talk true field to finish, what you're really saying is that not only are you getting all your numbers and everything, but you're also getting your picture. Okay, so it's the same thing, except now you're getting line work and things like that associated with it. Okay, so in order to do that in your data collector and in your codes out in the field, you have to set up things like, if you're locating stuff in the field like line work, you have to tell somebody, okay, this line, I'm starting this line here, and then I'm ending at line right here. Now I'm hitting a curve, and here's a PC and a point on the curve and a PT. By doing that with what are called codes, you can actually get line work that comes in. So then that is what they call true field to finish. Okay, does that make sense?
Yeah, it does.
I mean, otherwise, if you're just getting a point group, if you're just getting a bunch of points, you're going to get an XYZ position, which is really good. And then you get a description, but then somebody's still going to have to sit down in the office and string all the points together. Okay. So there is a bit of work that still has to be done. All right. And one thing I would say to true field to finish, I mean, it's not 100% either. There's still going to be something that's going to have to happen in the field or in the office to clean it up. Okay, so it's not going to be 100%. Does that also make sense?
Yeah, I'm starting to experience it a little bit at work, and like we had an instance last week where I didn't end at PT and it started connecting lines. We ran the field to finish. It connected one curb to one on the other side of the building.
Right.
We went in and cleaned it up, like you said.
Right. So it's and that wasn't the error of the data collector. That was human error. Okay, so it's going to do essentially what you tell it to do. And if you forget to do something like you said, then you get a mistake. Or, another common thing. Have you ever had a case where you booted the rod to a different HI, a rod height, and then you forgot to change that? You know what I'm talking about?
I haven't had it, but they like the foremans I work with talk about it all the time because I guess our boss's son did it last year and it caused a lot of headaches.
Sure, because what that does is that blows the elevation of those points from that point on. So, that can be a mistake. Now, I'll talk about this a little bit, but in your data collector, a lot of times you can figure out where that happened, and then you can go back and fix that stuff digitally and then rerun all that information. Okay, so hold on to that thought. We'll come back to it. Okay, so basically a data collector, it's just really essentially a small computer, handheld computer. It really has a lot of memory now because these guys will store tons of information, particularly if you're doing something like scanning technology, or the morning group didn't get to see the guy out there running the drone, but I had an afternoon group out there. He was flying a drone over the site and he was taking pictures, and those pictures eat up a lot of room on that data collector. So you have to have pretty much memory in a lot of these guys. So most of these guys are going to have now built-in software too that has all kinds of capabilities. Essentially, anything that you can do in the office, you can pretty much do in the field on the data collector, including draw pictures or build surfaces or, do your own layout calculations. So you have all of that. And then you have transfer capabilities. So you can take the data collector and take that information to the PC, and we call that a download. And if you're going from the PC to the data collector, so if you've got an office where they designed a bunch of stuff that you need to lay out, they can upload that stuff to your data collector, and that's called an upload. So it'll do both. A lot of the connectivity now has changed. Everybody know what Bluetooth is?
Yes.
What is it?
Yep.
What is it?
It's like wireless connection between devices.
Right, and it uses radio frequency. Okay, what it is. So, back in the older days when you had the data collectors first came out, they were connected with a cord from the data collector to the instrument, and those cords were really expensive, and the connection ends would break. I mean, realistically, guys that use these out in the field probably bought a cord at least every year, and they weren't cheap. So then they brought out Bluetooth. Bluetooth has connectivity wirelessly, okay, through radio frequency. When Bluetooth first came out, it had a limit of 10 meters. So once you got longer than 10 meters away, you lost connection. They pushed Bluetooth now, so they have a different protocol for it. So it can actually go a little bit longer now. But both devices have to have Bluetooth capability. So the total stations have to have Bluetooth as well as the data collector itself. So like those old total stations that we have, they still have old cable connections, and some of the newer ones actually do have Bluetooth in them, but the older ones definitely don't. So you can see that difference there. Okay, so a lot of people still use cords just because they've still got what they had originally. Okay, so your data collectors, they come in a lot of different styles. You have different internal units. And what that means is basically the total station itself can be a data collector. It's built right into the instrument with a typical SIM card or something like that. It's going to have real limited memory. And then of course, anytime you're using that, you're sucking power from the battery of the instrument as well. So, and plus the screens, you guys know those screens are not very big on those data collectors or the total station. So they're really hard to read if you're trying to look at anything, and pulling up a map on them is probably impossible. So those things don't make very effective data collectors. But all instruments do have that capability typically. If they're a total station of any vintage, about the vintage that we were using, they have data collectors in them. So the external units are a lot different. Now we'll show you some. I'm going to show you some on Thursdays. There's a bunch of them that are sitting around in room 101 that you can look at, but they're definitely ruggedized handheld units. Some of them are a little bit smaller than others. They typically have large amounts of memory, minimum power consumption, and they are going to use a standard operating system. Most of them use Windows CE. Now, when I say they're handheld, I mean some people run them on tablets that are sizable, but those aren't very ruggedized. So the problem with a tablet is it's not a very rugged system. The ones that are built specifically for surveying, we'll see on Thursday. They're definitely ruggedized. They're made to be out in the field in hot conditions, cold conditions, and they can tolerate rain and water as well. Although one thing, any of you guys use data collectors out in the field? Much? Casey, I guess you are, right?
Yeah.
Have you ever been out in a cold day? Real cold day?
Yeah. We were out. A lot of times we would, like, because I started there at the end of February, early March, and a lot of times we'd pull up to a job and we'd let the system power on outside and let it accumulate to the weather.
Right.
Like 10 to 15 minutes before we did anything.
Because the screens can actually be kind of lag behind because they're typically an LCD technology, and the weather temperature affects that, slows it down. So those can be an issue.
I've had problems with them too on in the snow. Like snow would be falling off the trees and the screens would get wet, and
Yep.
we had a lot of problems with that.
Yep, absolutely. Especially, what if it's a touch screen?
Yeah.
So that could affect that for sure, definitely. So in general, though, they're like I said, they're made to be beat, but they do, they still are somewhat delicate instruments. Now they come in all sizes, and like I said, you'll get to see some. But we actually, back in the 80s and 90s, a company called TDS, Tripod Data Systems, developed a set of programs that you could actually load into Hewlett-Packard calculators. And so, about these guys were data collectors that were just on a calculator. And actually they worked really well because the software was really well written. The calculator was really good calculator. It just wasn't ruggedized. But back in those days, a lot of surveyors used those as data collectors because they were a lot cheaper than the ones you get now. Now, a data collector is going to cost you, a minimum starting cost is going to be about $2,000. And you could get a TDS system. Your software was maybe $500 and your calculator was maybe $300. So that was a really good deal. And like I said, they worked really well. They had really good software. But pretty much nowadays, they're all the different external units. All right, so data collector, disadvantages of cost, okay? And that $1,000 is probably cheap. I would say most of them are probably priced around $2,000, probably starting. They're battery dependent, so if you lose power, you lose communication. You may lose data sometimes, so that's something you got to be real careful with. Connection to the instrument, as we talked about, cables, they will frequently fail. Bluetooth does have range issues. Like I said, initially when Bluetooth came out, it was 10 meters, but they pushed it, I think, to 100 meters now. And the one thing is, the software on the data collectors is not strictly intuitive. So there's a lot of screens and stuff you got to get into. So it takes a while. There's a learning curve on the software and data collectors, especially if you don't use it every day. Can you concur with that, Casey? That some of that's not easy.
Yeah, and then like we just hired a guy who used the data collector with his company he was with before, but it was a whole different software, and it's been taking him like a week and a half just to learn
Yep.
our stuff too.
Yeah. So it has kind of a steep learning curve, but once you get into it, it goes pretty quick. Now the other thing is too, as you just mentioned, every company kind of uses their own codes and the own way they do things. So not only do you have to get used to the software, but you have to get used to the codes that people are using. Because one person might say ground is a GRD and another group might say that it's just G. So as you're coding for that stuff, as you're locating it. So it just depends. And of course, those codes can make a difference when you're doing, like you said, what they call field to finish. That can make a huge difference. So these are issues, but in general, the disadvantages, the advantages far outweigh the disadvantages. So anybody that's really doing high level of work, I mean, that cost right there, I mean, you recoup that in a couple of jobs easily. And the fact is that, like I said, some of the instruments really can't run without them anyway. So you almost have to get them. All right, so data collectors can be used for a lot of things: layout, data gathering, and also then what we call coordinate geometry or COGO calculations. So I think I used that term COGO before, but when you hear that, that's what that references is coordinate geometry. So that's a type of program software. Yeah, essentially AutoCAD's more or less COGO program. It does coordinate geometry type stuff. And of course, as far as this course is concerned, the layout would be the more important thing to kind of talk about. So everything we've kind of done, any of these calculations or whatever, that would be done through the layout modes of the data collector. And data gathering would be another way of looking at that, would be mapping, gathering data that you're going to bring in and use, that engineers are going to use in the office so that they can create jobs that are then going to go out and be used. And kind of like, here's a good example of the layout modes that can be used. A lot of these data collectors now can take the actual raw AutoCAD files that the engineers are using in the office. Those things can be downloaded right into the data collector. So the guy out in the field has everything that the engineer does, and he can do his own calculations. And we were just looking at that roadway layout. The templates or the typical section that was used to do that stuff, what we were just looking at, that can be shown right into or brought into the data collector, and all of that stuff can be calculated for you directly. So when you go out and take a shot using a data collector in a layout mode, it knows what station you're at. It'll know what the cut or what the proposed elevation should be based on the profile. So you don't even have to look at your profile. You just know what station you're at, and it'll actually, when you shoot it, probably it gives you your cut and your fill right then and there. So you don't even have to mess with it. And hopefully we're going to get to see some of this we'll get to see some of this on Thursday as well. Okay, so layout, of course, would include just strict point layout location. So whether you're just giving a horizontal location, X and Y, or an X, Y, and Z, or you might think of that as northing, easting elevation. A lot of people that are using either robotic or GPS, essentially that's what they're doing. They're just setting points. Their control is coming from control points that are on the ground, or if you've got if you're using GPS, basically your control is the satellites up in space that are positioning for you with those. So you have to have really good models though to do this stuff. So all of that data that is generated in the office by your engineers or your architect or whoever, that has to be downloaded to your data collector and all of that referenced in to get that. This kind of stuff, if you're just doing straight point layout, X, Y, Z, you're not seeing much go on. You just see the guy walk around, gets his point, he puts his point in the ground and, he goes. So that's really easy. It's really automated things. Same thing with elevation. You can do cuts or fills or grading. You can use it for highway, station offset type of stuff, and then also what they call slope staking, we haven't talked about slope staking too much, but basically it's using those typical sections to get the elevations on those different aspects along it. One of the things they're always looking for is where the road is going to daylight into the existing ground. And that's where they use this concept of slope staking. If you're doing data gathering, you're doing mapping. So this is what Casey was talking about in that field to finish. You're getting point locations XYZ or northern easting elevation. Basically, you're really getting an XYZ, and your data collector is converting that. Then you can also gather feature of existing objects. So this is that field to finish concept where you can get ditches, curb lines, building footprints, catch basins. All of that stuff can be located and labeled and connected with lines, so that when they download this into whatever software they're using, not only are they getting the XYZ locations, but they're also getting the line work as we talked about. Not only are they getting lines, but it knows what type of line, whether it's a curb or it's a face of sidewalk, back of sidewalk, building footprint, ditch center line, whatever. The other thing that you'll use is what's called a description. So this is typically alpha data, or it could be alphanumeric. It's typically or strictly non-numeric. I wouldn't say it's strictly non-numeric, but it's mostly descriptive in the terms of alpha characters. But for instance, you can use like INV for invert, but you might say invert 12-inch. So you might have some numeric data associated with that. You can also use data collectors for creating control, for traversing and running level loops. And not only will it record your angles and your distances while you're doing your traverse, but when you get done, you can actually go through your traverse calculations, get your closure information, determine your precision, and then go ahead and adjust it. And that can be done all in the field. It used to be, like I said, you'd have to write all this stuff down, you'd bring it into the office, somebody would sit down and do all that stuff that we went through, generate coordinates, and then those would be given back. That can all be happening right in the field right now. The only problem with that is that somebody who's doing that has to make the decision whether it's right or wrong. So the person doing that needs to really know what they're doing, because the data collector will just take that stuff and roll with it. So it's just like any other software. Okay, so let's look at some coordinate geometry type things. We've looked at this a bit. So inversing, what does inversing mean? Who can tell me? Come on, guys. We've done a lot of inversing. Who knows what inversing means? Nobody can tell me
The
that?
opposite.
What's that?
Taking the opposite.
Not when it comes to coordinate geometry. Inversing means I have points out there, X, Y, Z. And if I go from point 1 to point 2, what does inverse give me?
That'd be the distance.
And,
That would be your bearing.
okay, so it could be direction, it could be distance. And if it's a 3D point, you could also determine
The elevation.
Yeah, well, let's think of this way, the delta Z value, okay? Yeah.
Yeah.
So, but you could use that to calculate elevation, so certainly, okay? So that's what, when we hear the term inversing, it means you've got points, and as that implies, and Carson, let me explain, as I say that, as it applies to coordinate geometry, because what you said is true. So when we say inversing, in terms of coordinate geometry, we're saying we've got points in an XYZ format, and inversing allows us to get distances, directions, and drops, if you will, differences in elevations between them. So the one thing we haven't talked about, I kind of mentioned this, is the process of what we call intersections. So this is where you can take two bearings and shoot them at each other, and where they hit, you can get a point location where you didn't have anything or you didn't occupy it. Same thing with a distance and a bearing, and you can do this with a distance. So these are guys are referred to as intersections. Now I'm going to show you a little bit about these, but I'm not going to expect you guys to be having to do this, okay? So there's a lot of math. It's not that hard, but these processes are easily done in a data collector. So I'll show you how you do that. Then another thing is what's called a resection. Any of you guys out there surveying ever heard that term, resection, or used it? Casey, have you ever used a resection?
Yeah.
Can you tell me what it is? Do you know?
What we normally do is when we're staking out a building for a subdivision, we've laid out all the roadways for the subdivision. We've done everything up to that point, and we know that we have either cut notches or center line nails inside the road.
Mm-hmm.
So instead of having to run a traverse, I can set up my robot in the middle of the property that we're giving them their building information for, and we can shoot two of our known locations. And the system will take it and put you where you're at and give you your angles and your distances to what you're laying out from there.
Correct. So what he said is true. It's going to give you the ability to set control wherever you want to without having control. Okay. Now, I do disagree with one of the things you said. You only use 2 points, you said, right? Is that correct?
Yeah, that's all we normally use.
Okay, so you're doing what's called a 2-point resection.
Mhm.
That's not a very good resection mathematically. It's not very strong. So if you can add a third point, do a 3-point resection, you get a better solution.
Okay.
So we'll talk about that here in a minute. So don't go back to your company and say, oh, we should be doing 3 points. But, technically, mathematically, it's a lot stronger solution if you do 3. But, go ahead.
This might be that third check is we'll normally check the setback before we put anything in the ground. So we'll check into the 2 points and we'll go off the blueprint and see the neat box of where the front of their porch is and check the right of way and make sure that we have the right offset.
Mm-hmm.
Would that be considered a third check?
No, not necessarily. What you would really need is a third control point. Like, so if you had 2 notches and an iron pin, okay, then you could use the 3. But you have to be able to see all 3 from the point that you're at.
Okay.
That's the difference, okay? So again, you can use 2 points. I'm not saying, but resection, be careful with these guys. What this allows you to do is establish control anywhere you want on the site, but you have to see existing control already. But 3 points is better than 2, okay? Just saying, all right? Level loops would be another thing that you can do, obviously, and then surface, creating a surface, creating area, and creating volume determination. All of that can be done in data collectors. I'm not sure what George is going to do with us, but one of the things it'd be nice if we do a little mapping. He can create a surface for you really quickly from that data while we're out in the field. So hopefully we'll get a chance to take a look at that. So let's look at some of these guys. So an intersection, we have 3 types that we talk about. Bearing intersection. This is establishing a northern and an eastern coordinate of an unknown point. And that point is a point that you've never occupied or can't occupy because it might be something that you can't set up on or whatever. So what it requires is 2 known points that have northern and eastern, and you're going to measure a bearing or a direction from each of the known points to the unknown point. So from a diagram standpoint, I think I got a diagram in here. Yeah, here we go. So in this case, for a bearing intersection, notice we have point A, which is a known point. So it's got known northern and easting. And we have point B, which is a known point, northern and easting. So if those points are known, what that means is you know the distance and you know the direction between them. So that magenta line, because those 2 points are known, that magenta line is also known. So everybody see what I'm saying there, right? So you have this point out here that you want to get a coordinate on, but you can't occupy it or you don't want to occupy it. But what you can do is set your instrument up at A, backside B, turn an angle to that point. That's all you need. You don't even need a distance, okay? If I could shoot a distance to it, it wouldn't be an intersection. It would be what's called a direct routine. So I just have a direction. So then I set the instrument up at B, backside A, turn an angle from A to the unknown point. And what it does is it calculates this bearing and it calculates this bearing in the data collector. And by shooting those 2 bearings at each other, you can essentially come up with this point. So it does a bit of math. What it has to do is it has to inverse this distance in this direction. By knowing this direction, you can calculate that direction. So if you can calculate those, I mean, you get an angle here, you get an angle here, and you can solve through law of sines, you can solve this point. So it takes a bit of math. If you're doing a problem like this by hand, it probably takes about 15 minutes to do. And a data collector, it just takes seconds. I think I have,
So
I
it
had some-
calculates that intersection point immediately.
yeah. Oh, yeah. Well, let me say this. You have to set up here first and then backside B and turn the angle, right?
Mm-hmm.
And then you have to set up at B backside A and turn the angle. So you won't get the intersection calculation until you've got both directions. Okay.
Of course.
Yeah. So once you do, yeah, it's pretty immediate. I mean, as quick as a computer calculation can happen, that happens all the time. Now, you guys do this in AutoCAD all the time. This would be an example of what we call a fillet with a 0 radius. So if you just in AutoCAD go and draw a line any direction and another line any direction, and then you fillet them together with a 0 radius, what you're getting is this point right here. Or a trim or an extend would be the same thing. That's basically a bearing intersection, okay? But we're doing it a little bit differently. But why this is a point you may not be able to occupy is because that could be the top of a radio tower. So there's no way for me to climb to the top of that radio tower, but I can certainly shoot an angle to it, okay? So this is why this kind of thing is pretty cool. And this is used a lot out in the field for a lot of different reasons. Okay, everybody okay with that? That's what we call, it's called a bearing intersection. Some people call it direction, because it makes kind of this more sense to say that typically, because not everybody works in bearings. So the other type of intersection that can be used is what's called a bearing distance intersection. And again, it's going to establish northern and eastern coordinates of unknown points for you. Again, just like the other one, this will require you to have 2 known points. So they have to have good northern and easting. You have to measure a bearing from one of the points to the unknown point, and then you have to measure a distance from the other point to the unknown point, okay? And that radius or that distance can be considered the radius of a circle or an arc. So the way this thing works, it can yield one of 2 possible solutions. So with this type of intersection, you kind of have to know what the solution is or which of the points you're looking at kind of up front. And on a data collector or on a computer, a lot of times it'll have you pick. It'll give you both solutions. It'll say, which one do you want, or do you want both? So you're typically not looking for both solutions, just one. But if we look at a diagram, this is what's happening. So again, there's my known point A, northern and easting, and known point B. And notice from A, we are measuring a direction. So now if C is the actual point I'm after, notice there's a second possible solution here. So notice the good point and the bad point lie on the same line. Everybody see that? And if we think of this being the center point of our distance, and you think about swinging a giant arc, and that's what that cyan is. So if I swing that arc at that distance, it's going to intersect that line here, but it's also going to intersect that line there. So in this case, there's 2 possible solutions. And if I'm looking for this one, I have to make sure I pick this one and not this one, because both of them would be valid for this type of thing going on, but only one of them is what I'm after typically. You guys seen how this works?
Yep.
Okay. So that's what we call a bearing distance intersection, or again, you could call that a direction distance intersection. So the third type of intersection is referred to as a distance. And again, it's going to give you unknown points coordinates, and it requires, again, 2 known points and then 2 known distances. So the radius distance from the first point, the radius distance from the second point, and again, this will yield 2 possible solutions. So another name for this is arc intersection, because what you're actually intersecting is 2 arcs or 2 circles. So if we look at this example, here's your known point A, known point B, your known distance. Notice I'm swinging an arc from point B, and then I'm swinging an arc from point A here. And where these intersect, I get a solution here, and I get a solution here. This one's actually one of the easier ones to calculate by hand. It's probably not as involved as the other 2. And what you get here is if you connect a straight line from A to B like this guy and this guy are going to be mirror imaged about that line. So one's going to be kind of, in this case, north, and the other one's going to be due south of it, essentially. So again, you kind of have to know which solution you're talking about. Now, how many, you guys all know what GPS is, right? So this is essentially exactly what GPS does to pinpoint your location. So you can think of this as one satellite and that is another. And what it's doing is you've got your receiver sitting here and it's telling you, or it knows how far it is from the satellite to the receiver and from this satellite to that receiver. But the problem is you're not intersecting arcs with GPS, you're actually intersecting spheres. So what's happening, you're getting a sphere, this represents a sphere and that does too. And where those intersect, you got a circle here. So you got not just a 2-point uncertainty, but an infinite number of uncertainties. So that's why you're going to have a minimum of 3 satellites. If I put another satellite out here, and that sphere will intersect the other 2, and where that comes in, then that gives you a better point. But normally with GPS, you're intersecting like maybe about 10 to 12 satellites now with all the satellite availability. So the more satellites you get, the better your solution is. You see why I was getting at 2-point versus 3-point, Casey? Maybe.
Yeah, I get it now.
Okay. Well, it's not quite the same, but there's more uncertainty with just 2 points. Okay. So that's a problem. So this is called a, go ahead. Go ahead. Listen.
Basically, there's more room for error with just 2, and that kind of helps eliminate it all.
Exactly. Or it helps proof if there is some error. Yeah. Because if you just, all it would take is one not real great angle or one shot distance wrong, and your solution is going to be different. And it doesn't take that much to be off. But with a third one, you're getting a tighter solution. Yeah.
So when you were saying that if you were to look at your data, just looking at the raw data, you would know where your error is.
Well,
would that
you
be
might
related
know-
to this?
Let me say this. If you go into your raw data, you might know where it occurred. Okay. Here's an example of that. So let's say you're out in the field, and normally when you're running a data collector, you set your rod height to a certain value and you leave it at that. So let's say we set our rod to 5 feet. So we're out there gathering all this data, or we're grading stakes with a 5-foot rod, so everything's working fine, right? But you get to a point where you can't see that rod because you're shooting through a tree, like we've seen some of that issues we've had. So we raise the rod up, maybe to 6 feet, just to take that shot. So you go into the data collector and you say, now your rod is at 6 feet, okay? So then you drop your rod back to 5 feet, but you forget to change it back to 5 feet in the data collector. You see what's happening there?
Yeah.
Everything from that point on is wrong by 1 foot. So in your raw data, you can go in there and tell where you set it to 6 feet, but didn't change it back. So you can go back in your raw data and you can say, oh, I want it to go back to 5 feet from this point on. So you can do that and then reprocess it and it'll recalculate everything for you. Does that make sense?
Yeah, that makes sense.
So there's a lot of other things you can do, like, that's just one example where that would occur. And that, by the way, that happens a lot. That's not an uncommon thing. People do that all the time. Or they'll get the wrong back. Here's another example. You could set up at point A and say in the data collector you're backsighting B, but in reality you're backsighting E. So all of the shots then are going to be rotated by the difference between the one azimuth and the other. So again, you bring that into your picture and nothing's fitting right because all those points are rotated with respect to where they should be. Well, that's an easy fix. You can just figure out what you backsighted wrong, and then you can just rotate it based on the rotation angle. So those kind of things, those are pretty easy fixes when you get to raw data. Yeah. Okay, does that make sense?
Yes.
Okay, cool. All right, so here's a resection. Here we go. This allows you to establish a control point, okay, any point on a site. Now, with a resection, by the way, you can get both horizontal resections and vertical resections. And as is typical with a lot of the things we talked about, just like with trigonometric leveling, a vertical resection is not going to be as good as a horizontal resection. So you're going to get better results X and Y or northing and easting than you are going to get your Z value if you're doing this. But for a 3-point resection, you have to have 3 known points. So they both, that means they have to be good points and they have to have a good northing and easting. And the point that you want to establish through the resection has to be visible from all of those 3 points. So in other words, when I'm setting out in the middle of a field, I have to be able to see point 1, point 2, and point 3 in order to do this. You have to then measure angles from known point to known point, and then you also shoot distances typically, okay? And this can be used exclusively or extensively for layout. A lot of people in layout use this, but again, some people probably shouldn't be using it for certain things. It's not perfect, okay, the way it works. But here's an example of a 2-point or a 3-point resection. So I have this point D that I want to establish here. I don't have coordinates, but I do have this point A, point B, and point B. So these are known. They have northing and easting, northing and easting, and northing and easting. So your data collector, you tell it you want a 3-point resection. It'll ask you to shoot this point, and then it'll ask you to turn this angle and shoot this point and shoot this point. And by being able to calculate, it can inverse that distance and direction and that distance and direction. And by the angles and distances that you shot, it can calculate the position of this point. You can see though, Casey, if I take this point away, that's a lot less strong than it is by having 3. Can you see that?
Yeah.
And even some data collectors will probably, I think they can go up to a 7-point resection. So it's just like anything else. The more points that you can add that are good, probably the stronger the solution as opposed to less, okay? You would never use 2 satellites to get a position. That's a little bit different case, but you would never use 2 because you have to pretty much use 4, but it just kind of gives you that idea. The more you can add, the stronger the solution will be. Now, depending on what you're doing, I mean, if you're just doing a building layout, that's probably fine. You're probably getting a great position. It's not a big deal. But even so, even having this point, sometimes I'm going to try to check that independently. Like you mentioned, measuring to something else. Well, if you had another control point out here you could shoot to, you could just check in that way. So there's always other ways to check it. Okay, so let's take a look at some data types. Go ahead, listening.
Usually when we do a resection, it'll tell us our correction, like after if we do 2 points. And I don't want to throw VX underneath the bus, but if it's within like a couple hundreds, we usually roll with it. But
yeah, and that's what I was saying. It depends on what you're doing, you know. And I'm not saying you're throwing anybody under the bus. Mm-hmm. I'm just saying, you know, depending on what you're doing, you got to be careful. You got to look at what it's telling you the error is, or essentially it's kind of like a precision. And, you know, you wouldn't want to use a 2-point resection for high level control though, okay? You just wouldn't want to do it, all right? But if, you know, you're doing certain like building layouts or something, yeah, I can get by with that. That's not a big deal, okay? But think about that next time. Yeah, you ought to do that as a test case too sometimes and try a 2-point and a 3-point if you can see 3 points and see if you get a different solution. You'll probably see it's slightly different with the 3-point, okay? All right. So data collectors usually work in 2 types of data. You have what's called raw data and coordinate data. The raw data is what it captures directly from the instrument, and then that is saved. And this is the stuff that can be edited later after the fact. It does increase memory usage. So some people will turn their raw data section off in their data collector because if they have smaller memories, they don't want all that data in there. The coordinate data is the stuff that the raw data is taking and converting into a coordinate of some type. So it takes all that raw data and it converts it to a coordinate for you. So if you turn off your raw data, you won't have the ability to go back and check whether you've made mistakes like rod shots or anything. Then you're just kind of screwed because what you're getting is just an XYZ and a description for each point. That's it. So a lot of people are working in both raw data and coordinate data so that you can capture that raw data and you can use it later down the road. But at the end of the day, what we're after is just that coordinate data. Okay, that's the primary thing. And typically when you're downloading information into your software in your office, you're downloading almost exclusively coordinate data. Unless you have line work, then you would also be doing line work. Okay, so your raw data consists of basically just directly captured data from the instrument: slope distance, zenith angle, and horizontal angle. So those are the three things that you essentially need to establish points. So your raw data will also consist of stuff that the operator inputs, okay? So the data collector has to know what point you occupied, okay? Or if you don't know the point numbers, you can input a northing and easting and an elevation value. It has to know the back site or an equivalent northing easting elevation, height of the instrument, which you have to measure and put it in, and the height of the target, and then any description. So all of this stuff is input by the operator. So you can see there is still a large source of error right here. Again, transpositions could be going on. You enter a wrong northing value or an easting value, you know, the height of your target, your rod height, you know, those are all things, those aren't coming from the instrument. So that can still happen, and it does. Okay. Then your coordinate data is primarily just your raw data that has been converted. So it's essentially taking a spherical coordinate, which the raw data is giving it, and it's going to convert that spherical coordinate into a rectangular coordinate, northing easting elevation, or if you're working in highways, that could be possibly station offset elevation. And then you can also alternately add description information. So here's a good example of what's happening out in the field. So if you can kind of envision this, we are set up right there. That's the bottom of the instrument, and you've got the zenith coming right through it. There's your total station. You have a back sight in this direction. So that's either given as an azimuth, or you actually know a point you're sighting on, but this thing is known somehow, either through coordinates that we've calculated or put in there, or we've got 2 points that are in the field. So we would take a shot, zero this out, you zero your back sight. If this point right here is the point that we're after, that foresight, what you're doing is you're measuring the horizontals at horizontal distance. The instrument is measuring the slope distance and the zenith angle to the target. So to get to this point, it has to first take that slope distance and convert it to a horizontal distance. And then if it knows the horizontal distance and the horizontal angle, it can calculate using the azimuth. It can calculate the azimuth of this, which gives you a latitude and departure. So ultimately, then you can calculate the northing and easting of that point. And by using, again, your zenith angle and your slope distance, you can calculate a vertical difference between the total station and the target. And you can take the HI plus the vertical difference minus the target reflector, and that'll get you the Z value. So based on what I just said, all the stuff we've talked about, we've looked at different things of this, but we've talked about all of this kind of stuff before. All of that happens within seconds. After you turn that angle and you shoot that distance, and that data collector just spits that point out, it went through all of that math. It did a lot of high-level calculations to get you that point. Okay, so this would be an example from your data collector. What you would be getting is a zenith angle of this, 82, 12, 30, slope distance of this, and a horizontal angle of 280, 30, 30. Now, realistically, you're not even going to see any of this information, because the minute you turn it, it's just going to pretty much gather that. And what the operator is going to input is that, okay, I'm sitting at a point, I'm 5.6 feet above it, my rod is at 5.6, my backside azimuth is 30 degrees, and that might come from actually saying I'm at 0.1, backsighting 0.2 kind of thing. And then your occupying points at 2,000, 2,800. So from the instrument information and the operator's data information, what it's doing is there's your azimuth, there's your coordinate value information, there's your angle that you turned, there's your zenith, there's your slope, rod, target heights. Actually, I think that should be 5.6, not 5. So what that does is that gives you the solution of point A right there of that elevation. So, again, a lot of math, but it would spit as quick as you would turn that and shoot that angle and distance, you would get this spit back out at you in the data collector, and it would record that point. So you can do multiple points in a day, probably thousands of points, in a day if you're quick. Okay, when you transfer data, data transfer is the process of transferring from your data collector to your PC. Like I said, now you can do that remotely over the internet. So you could be you could be out in Kansas and you could be sending this stuff to your office in Cincinnati. But even if not, then a lot of times the guys will bring the data collectors in at the end of the day. They connect them into the PC, and then they transfer that data from the PC or from the data collector down to the PC. I'm going to tell you, this process right here, transferring data, is one of the biggest issues, and it's not real seamless unless you're using the same kind of software in the data collector and the same kind of design software. It's a little bit of hoops you got to jump through. It's not real simple. But when it works, it just downloads really rapidly. You get all your data, and then that can be used for design, calculating maps, any kind of verifications, all of that good stuff. But yeah, just be forewarned, if you've ever seen anybody transfer, it's not real simple. It's getting easier, but it's still probably one of the harder things that happens. And you can then take your design information and transfer it back up to the data collector. So, you got engineers that are working on sites, developing whatever, and bring all that stuff up to the data collector, and then you got it out in the field. And like I said, a lot of data collectors will even take AutoCAD files now, which allow you to do all kinds of stuff. Okay, so the data collector transfer from your data collector to the PC does require software to download from the data collector to the PC. So even though the data collector has software, the PC has software, there's usually a little interface software between the two that allows them to connect and also does the download process. So it's not real simple. So if you import field data to your CAD software for design, a lot of times we talked about, that's called field to finish. And a lot of people that are doing this field to finish process are AutoCAD Civil 3D, Carlson, and Revit. These guys are all what they would call field to finish softwares. But in order to do true field to finish, the guys out in the field have to do a lot of work. Okay, that has to be set up. It's not that simple. So once you get your codes and your line work and all that done, then this works a little bit easier. But it's still not 100%. Even if you have probably true field to finish design that a lot of these guys are doing out in the field, there's still probably 20% of the work that has to still happen in the office or more to get what you need out of it. You can also just import straight points, or you can import line work. So all that's all critical. All right, so if you're transferring from the PC to the data collector, you do have to have the software to upload, go both ways, and export software. And you can export all kinds of things. Like I said, you can export Civil 3D files, Carlson, Revit. You can do plans and profiles, surfaces. Some of the file types that they use are .dwg files, which would be AutoCAD files. DXF are drawing interchange file formats. That's basically a language that is used by a lot of different CAD vendors. So if you're working in, let's say, AutoCAD, or let's say Civil 3D, and you want to convert it to Carlson, they won't read each other's data direct, so you have to create this intermediate file called a DXF. And then this other one that people use a lot is called LandXML. So an XML file is extensible markup language files. That information can also be brought in to data collectors or vice versa. And typical section template files, these guys can be brought in and out. So most of your data that you're working with in your design platform can be uploaded to your data collector. So the bottom line on that. All right, so that's kind of what we're getting into. Does anybody have any questions for me? I'm going to go ahead and stop the recording.